Hey guys, Miss Marisic here, and in this video we're going to talk about titration curves. Now, a titration is a process that we have previously discussed back in Unit 4, so some of this is going to sound familiar. So as a reminder, a titration is a technique that is used to determine unknown information about some sort of reaction. And what we'll have is a solution that is in a burette. As a reminder, a burette is a tall piece of glassware that has milliliter markings all down it. And at the bottom, it has a valve that we can turn. And whatever solution that's in the burette is known as the titrant. And what we'll do is, using the valve, we'll add that solution drop by drop to our other solution, which is typically in an Erlenmeyer flask below the burette. And that other solution is known as the analyte because we're trying to analyze some sort of information about it. And so what we'll do is we'll add those two together drop by drop until we reach what is called the end point of a titration. Now, the end point is where whatever indicator we have used in our reaction changes color. So the end point is tied to a color change in the titration. Now, some reactions will naturally change color on their own, and so I don't need to add a separate indicator. We might have a product that has a very distinct color to it, and so therefore it'll naturally do that color change for us. But often we're using solutions that are clear and colorless, and the product is clear and colorless. And so without using some sort of indicator, we're going to have no idea where that endpoint is at. And so the indicator is super important to make sure that we add. But it's also super important to make sure that we're picking a correct indicator. If we've used a correct indicator, then the color change can indicate where the analyte and titrant are perfectly reacted with each other. And what that means is that stoichiometrically, they're canceling each other out. We have no excess reactant remaining in our analyte container. And so when we've reached that point, we call it the equivalence point. Now, if we've picked a good indicator, the endpoint, which is tied to the color change, will occur at the same time as the equivalence point, where the stoichiometric ratios cancel each other out. So we have to make sure we're picking a good indicator. It's important that the endpoint and the equivalence point are happening at the same moment. And so we're going to talk about picking a good indicator here in just a little bit. Back in Unit 4, when we previously did titrations, usually the goal of the titration was to figure out an unknown molarity of our analyte. And so what would happen is that you would have your titrant in your burette, where you could take an initial volume of it, you would know the molarity of it, and you would add it to some sort of known volume of your analyte until your color change occurred. And so once that color change occurred, you were looking for the exact drop that changed the color, you would stop the process, you would record your final volume of your titrant, and then you would use all of that information, your two volumes and the molarity of the titrant, to figure out your molarity of your analyte. That was the goal of a titration previously. However, in this unit, we are actually going to use a titration for a different purpose. We are actually going to be using our titration to figure out what is called a titration curve. We're going to be concerned with points all along the titration process, not just the equivalence point itself. So we're going to be kind of doing this from a different perspective now. Okay. Also, I do want to mention that with an acid-base reaction, the equivalence point is where the hydrogen that's coming from the acid is completely reacted, so again, stoichiometrically canceling out, with the hydroxide from the base. And so it's the point where we've perfectly neutralized those two ions out to make water. And so a correct indicator would be one that changes color around the same pH as the neutralization. Now, we're going to talk a little bit today about strong acids with a strong base. And if I'm using a strong acid with a strong base, then the pH where they neutralize out should be 7. However, if one of those solutions had been weak, then no longer does that necessarily occur at a pH of 7 because you're going to have a conjugate present that could end up changing up that pH level. And so we're going to talk more about that weak with a strong situation on another day. So this is not the only day where we're going to be talking about titration curves, believe me. Now, a titration curve itself shows what happens with pH of the analyte as the titrant is being added drop by drop. So it basically shows what's going on with that pH level all throughout that titration process, both before we've reached the equivalence point as well as after we've reached the equivalence point. Now, to construct a titration curve, you could do so with calculations, which is what we're going to do today. Or if you were doing this in lab, you could use some sort of pH probe or a pH meter to do that measurement. We have pH probes that we can connect to our CBL probeware stuff, or you could use a standalone pH meter. There's ones that kind of look like almost like a thermometer, only it's not. The little meter on top just tells you what the pH is inside. So that pH probe would be our way of getting that pH information in a laboratory setting. So to kind of get a better idea of exactly what is happening when we do a titration curve, what we see here is our setup that we would be utilizing in lab. So we would have our burette with our titrant in it and our flask down here with our analyte that we would have added some sort of indicator to it so we can tell when we've reached that endpoint, and we can assume that that's at the equivalence point. Now, in this particular setup, our titrant happens to be a base and our analyte happens to be an acid. So imagine that there was a pH probe in here where we were recording the pH all along this process. At the very beginning, before I've started adding the base, I would just be measuring the pH of our acid. And so if I was to construct a graph where I was measuring pH at the very beginning, that pH would be very low because remember, acids have lots of H+, and so their pH ends up being a low value, way below 7. And so then what we're going to do is we're going to drop by drop start to add that base into it. We're going to start to add that titrant. And so that's what you see along this axis here is how much volume of the base has been added. And so you see as we start to add more and more of the base, the pH starts to inch up. Now let's think about why for just a minute. If I have all this H+ down here, the base has OH, and so as I start to add that OH and it reacts with the H and changes into water, that amount of hydrogen ion is getting smaller and smaller, and so that pH starts to increase up. Now, at some point, what's going to happen is that all of the H ions in this acid are going to be paired up with enough base hydroxide ions. And so when those two perfectly cancel each other out, we end up reaching what is called the equivalence point. So it says here at the equivalence point, the hydrogen and hydroxide ions equal each other out. And as long as we picked a good indicator, your indicator should change color at that point. Now, you notice at the equivalence point, we kind of get a very distinct shape here on our titration curve. Like we're kind of gradually changing. And then all of a sudden at the equivalence point, it boop, pops up really fast. So keep in mind that these titration curves have a really distinct shape to them. And so that kind of helps us to figure out what's happening on this curve, exactly where that equivalence point would be. So then what would happen is all of the hydrogen has been used, but I still continue beyond the equivalence point to continue to add base. And so that means now I'm starting to build up excess hydroxide in here. And so as that hydroxide builds up, my pH continually starts to increase until at some point it reaches a maximum value that it can't go above. And so you can see, again, that creates this very distinct kind of almost S shape to our titration curve. Now, this one is showing a strong acid with a strong base. And when you're doing a strong acid and a strong base together, your equivalence point should happen at 7, and you should get a very clear increase right there in your titration curve. However, when you're doing weak acids and a strong base, or maybe a strong acid with a weak base, that pH may not be perfectly at 7. And the reason why is you might have a conjugate present in there that's going to change that pH level to be a little bit off than 7. And so that can slightly change the shape of the curve. Usually with a weak, strong combination, this S shape of the curve is not quite as pronounced. And so we'll see that on another day, how that curve changes depending on what kind of combinations I'm putting together. Now, I want to talk about picking a good indicator for a moment. So with that said, let's go ahead and flip the page and talk about selecting an indicator. Now, we do have some solid indicators of pH. Some of you might remember back from pre-AP using litmus paper. Litmus paper is this kind of tester paper. Those of y'all that have a pool, you might have tested your pool water with litmus paper. Litmus paper is red in an acid and blue in a base. We also have pH paper, which you have to have like a kind of a scale to use to figure out what color we have for which particular pH level. However, when I'm doing a titration, it would be really annoying to keep on having to put papers into that solution. Obviously, a pH probe or a pH meter would be way easier to measure that exact pH. However, if all we're trying to do is figure out where the equivalence point is at, then we can just use a liquid indicator just to know that point. Okay, so we want to pick a liquid indicator that we could just drop into our solution, so much easier than a paper, so that we know when we reach the end point of the titration, because again, that end point where the color changes should be the same as the equivalence point where the hydrogen and hydroxide have canceled each other out. So here's the deal. We have a whole list of indicators down here on our page. You notice there's all kinds. You notice they have all kinds of various colors to them, but then you also notice here a pH range. That pH range shows where these particular indicators change from being one color to the other. Now, the reason why we have so many various ranges is because not every solution reaches its equivalence point at 7. If I have a strong acid and a strong base, the equivalence point is 7. And so if being 7, I have a couple different options that I could use on here in order to figure out what the best indicator would be. However, if we have a weak and a strong together, maybe a weak acid with a strong base, that equivalence point is not necessarily occurring at 7. And so that's where some of these other indicators might be better to use. One other thing is that even though on a strong and a strong, the equivalence point is 7, we noticed on the previous page that we had a very dramatic change from a pH of 5 to a pH of 9. Like if you look back to that previous picture, from a pH of 5 to a pH of 9, I basically hardly added any base, right? Like, I mean, I didn't have to add anything there to get that to pop way up. So honestly, if I'm just trying to figure out that volume of the base, I could change colors in quite a wide variety of pH levels there and still be considered a good indicator. And so for something like that, where we're looking for that pH to change at around 7, but it can do a little bit more or a little bit less, you notice looking at this list, we have several different options for that. So you could use methyl red because this changes at about 5 to 6. So that would probably give you, be a good indicator to use. Bromothiamyl blue is a great one. You notice its pH range is 6 to 7.6. So that would really be in that 7 range. But even like this phenol red is not so bad. I mean, and even this thymol blue's second change would work. So, you have some choices here. And the reason why we like having all these options is because sometimes, we don't have a particular indicator. Honestly, I don't think in our stockroom we have thymol blue or bromoresyl green. I know we have phenol red and bromothiamyl blue and phenolphthalein, but a lot of these we don't even have. So sometimes you're limited by whatever choices you have. Okay. One of the other things that they typically give us on these indicator questions is that they will give you what is called the pKa of the indicator. Now, technically, this is the exact pH level where the indicator will change color. Okay, but it'll do so really anywhere in these ranges. This is just the perfect point for that indicator. So again, we want to make sure that we are picking an indicator to use where the pH range or the pKa is as close as possible to whatever our equivalence point should be for our reaction. All right, let's go ahead and look at the next page and talk about two titration curves. So it says here are some sample strong titration curves. Both of these are a strong acid with a strong base. The only difference between these two is the direction that they're doing the titration in. So you can see in this titration setup here, they've actually added a pH meter. This is kind of an old school one. We would use one that is, kind of a little more fancy and a little smaller. But you can see it runs a cord with our probe into our solution. So as you're performing the titration, you would just leave the probe in and constantly be monitoring that value on the meter itself. Now, in this setup here, the HCl is the analyte. Why? Because it's in this beaker down here. The NaOH would be our titrant. And so you can see it's in the burette that we're adding. So if I want to think about for this setup, what my graph would look like, my titration curve. If I'm first measuring the HCl down here, the acid, then I should be starting low on this graph with my pH and end up increasing as I start to add the NaOH. However, if I was working in the opposite direction, so let's say I flip-flop these where the NaOH was in the beaker and the HCl was in the burette, then that means my meter would initially be measuring the NaOH. And so therefore it should be starting high on the pH and decreasing as I add the acid in. So you notice on these, we've kind of flipped-flopped here what we're adding to the other thing. So it asks us for some questions down here. It says, on the curve on the left, which substance would be considered the analyte and which one would be considered the titrant? So if you look at your graph up here, you should be able to kind of figure out what's going on. Knowing that I have HCl and NaOH, if it's starting low, then that means that whatever was originally in the analyte container to begin with must have been the acid. And I can see that the volume of NaOH is being added, so that had to be our titrant here. However, on this other curve, I noticed my pH was starting really high, which means my analyte, whatever was in the container to begin with, must have been the NaOH, and then I'm adding the HCl, the titrant, from the burette to get that pH to decrease. So just be very careful. Kind of as a hint, if you ever see your graph already constructed for you, then your titrant should always be on this bottom axis of your titration curve. Now the next question asks, what are some similarities between the two titration curves? Hopefully we notice on these strong titration curves, both of them had an equivalence point at a pH of 7, which makes sense. I mean, I'm adding the same things together. I'm just doing so in the opposite direction. Also with these both being strong acid, strong base combinations, I see a really steep increase in the curve at the equivalence point. So again, these are some common traits that you would see in a strong acid, strong base combination. Now on the next one, it says, using the table on the previous page, would you expect methyl orange, methyl red, or phenolphthalein to be a better indicator to use in this titration? And so what I would do is I would go find those three indicators on here. Okay, methyl orange I see is going to change color around 4.2. Methyl red is 5.0. And then, what was the last one here? Oh, phenolphthalein Phenolphthalein does so at about 9.7. So if I'm trying to pick the best one, and these are my only choices that I have, then what that means is that methyl red is probably going to be the best choice. Even though it's a little off from 7, again, its pKa there was 5.0. That was pretty close to 7. And because we get that dramatic increase right there at the equivalence point, it's probably going to change color pretty close to where it's supposed to. So methyl red would definitely be the best indicator to use out of those 3 indicators if I was doing a strong acid, strong base combination. All right, I hope we're feeling a little bit more comfortable with recognizing what a titration curve is. If you have any questions or need any help, please feel free to email me. Bye, guys.